Sure. Yeah, let me share my screen so everybody can see.
If you're going to share yours, I'm going to have to reshare again then, right?
Yes, JD. Yes, please. Okay, well, it's amazing your background, JD. I'm totally impressed. I'm gonna read it so everybody can see why we are so proud to have you in ASQ El Paso. Look, JD is an innovative business executive driving operations, performance, continuous process improvement, and global productivity. Excellence to develop the best class and award-winning. See? Can you read it?
Yeah.
Okay, yeah. So, award-winning in quality and lean management systems. I'm gonna jump to the JD's ASQ fellow, Shining medalist, certified Six Sigma black belt, certified manager of quality and organizational excellence, and certified quality engineer. IRCA ISO quality systems assessor for 10 years. How about that? Supported the MI Quality Council as a senior assessor for 3 years. Master black belt step ahead awardee. Impressed. That's impressive, JD. Initiative drive and delivers results in global manufacturing and distribution companies, encompassing operations, engineering, and new product development, guarantee maintenance and environmental health and safety, sales and marketing, finance and human resources. Industries include automotive, electrical, plastics, aerospace, coating, metal forming, and food. Super.
And she is inducted to Women in Manufacturing Hall of Fame too.
Okay, Hector. He's a co-author of several texts in quality management and Lean Six Sigma. International speaker, no question about it. Sharing Lean Six Sigma principles and techniques. Specialist, Six Sigma Master Black Belt, quality management systems, including Baldrige, right, JD?
Oh, yeah.
How about
20
that?
years of Baldrige.
Wow.
20 years in Baldrige. Wow. And I'm impressed also about this area, regulatory compliance for automotive, aerospace, and food. Outstanding. Well, you can read it yourself, but it's absolutely impressive, your background, okay?
Yeah.
So I know that any people in the industry would like to meet you, no question about it. So that's all I want to say. So go ahead, JD, and we are waiting an impressive presentation about design of
waiting for an impressive presentation too.
DOE and Mask, okay? And trying to remember your previous presentation about the symbiotic relationship between CPK and MSA. That one was a good one too. So please go ahead, JD.
All right, let me know if you can see my screen, okay?
See the first screen, yes.
Okay, I'm trying to get it to. All right. So one of you guys will let me know how many people we have totally at the end of the session, so that'll be helpful for me.
Okay.
Hi, everybody. I'm JD. does not stand for Jack Daniels. It's hard. I've never been drunk. But anyway,
That's
we're
a
going to
good
talk
one.
about
That's a
design
good one.
experiments. Yeah.
That's a good one.
We're going to talk about design of experiments. And for those of you that are on the call, it'd be helpful if you had a piece of paper, pencil, and a calculator. Your phone will do. You just need to add, subtract, multiply, and divide. So we're going to talk about the basic overview of a DOE. And we're going to break down the basic steps of conducting a design of experiments at 2 levels, something at high and low, with 3 variables, 3 different features that we're looking at to see what kind of answer we get. And the formula for how many experiments that is the levels to the variables. So L to the V. So if I have 2 levels and 3 variables, that means I'm going to need 8 experiments. And we will be interactive as we go through this. So I want to show you, this is what we call a 2x2. This is a little one. And in this case, I want to look at our shoe size. Most of us have feet, and they have a certain shoe size when we go out and buy new shoes. And we want to know if it's dependent on whether we're male or female and how tall we are. So the response or the output that we're looking for is how big is our foot. And we want to know if it's dependent on, our gender and our height. And in this case, I would have 2 male and 2 females. I'd have 2 guys and 2 girls. And I'd have 2 short people and 2 tall people. So I'd have a short guy, a tall guy, a short lady, and a tall lady. And you see these -1s and +1s in here. And what you do is you select which one is going to be what we call the low level, and which one is going to be called the high level. And the low level is the -1, and the high level is the +1. And you can reverse it the other way around. It doesn't make any difference as long as you're consistent that it's the same. And this is what we would call a 2x2. So this is 2 levels, 2 squared, 4 experiments. And these are the 4 experiments that you would do. I would get a short guy and get his shoe size. I'd get a tall guy and get his shoe size. I'd get a short lady, get her shoe size, and I'd get a tall lady and get her shoe size. And you see that AB, and that's what we call the interaction. So if I've got a short guy, which is what we're looking at for of one of the experiments, I would try to a couple of them so that I could get some data to start to see if these 2 things have an effect on each other. And you can do this in real life. It's a lot of fun to do, but we're going to spend our time doing a 3 variable. So this is what a 3 variable would look like. And I am going to turn on my pointer options, my laser pen. So here I've got 3 variables. I've got the first one, A, B, and C. And in my first variable, I'm going to have the first variable set 4 times at the low level, whatever that level is, and 4 times at the high level. For the second variable, I'm still going to have 4 times set at the low level, but you can see the pattern: too low, too high, too low, too high. And then I've got the third variable. Again, I've got 4 of them set at the low level and 4 of them set at the high level. Now it's low, high, low, high, low, high. And I try to color code these, and most software do color code these for you so that you can see whichever way you designate as the low is going to be shaded one way or the other. But then this way you can visually easily see what the low setting is going to be and what the high setting is going to be. And we'll be doing a real one of these in here so you can see the data and how it works through. This AB, these are the interactions. Each variable by itself would be something that maybe has an effect on my end result. So AB would be the interaction, and here I would have 2 negatives, and that interaction would end up being positive. And this is what Taguchi ended up coming up with when he started doing design of experiments. He found these patterns out, and he put them into a couple of tables like this so that we could run our experiments, get the answers out, and then see which things are affecting the others. I could see the A by C interaction, a -1 by a -1, and that's a positive again. And then I could look at the BC interaction, which is a -1 times a -1, and that would be positive again. This is how the table is set up. And we'll go through this step by step to see how that works. When we look at a design of experiments overview, it's a guide for planning and conducting those experiments. That's all we're going to do, is how do we make the experiments happen? Some of the outputs that we want to look at, for example, I was looking at the size of a foot. You know, what kind of shoe size do I wear? That's my output factor. But if I was in my manufacturing facility, I might be looking at my pass or fail, my yields. I might be looking at a desired dimension. I might be looking at attributes like does the thing have a hole in it, or the size of porosity. I might be looking at speeds and feeds in terms of efficiency. These are the things I'm trying to look for and to get an optimized result on. But a lot of different inputs can go into it. Temperature, speeds, technology, material types, all of these different input variables. So some of the pros of doing a design of experiments is it's a planned testing format, and it does save you a lot of time and money. One of the biggest things that people get sucked into doing is if I've got a lot of variables, they often do what we call one factor at a time testing. I'm going to hold one fact. I'm going to check one factor and keep everything else the same. And I'm going to turn my factor on low and turn my factor on high and see what happens. And that's good. That works. It just takes more experiments than if you would do it in a design of experiment manner. And so this is where it really allows you to save time and money. And it can help you identify the optimum settings for your process. Now, some of the cons of doing a design of experiment is you'd have to know how to do one of these. It takes a little brain matter. And, you know, it's usually helpful to have some software, whether you're using Minitab or SQC Pack or whatever tool you're using. And you can do these just as easily in Excel. The math works. And you need to have somebody experienced to do that data for you. So any design of experiments approach, the first thing that you have to do is a measurement system analysis. And I've got it first. And I got first 3 times because you have to do an MSA first. If you want to do a design of experiments and you don't do an MSA, your design of experiments will be garbage. I have seen so many times people put a lot of work and effort into putting in a design of experiments, and they did not do an MSA. And because of that, the data was really suspect. So if the data isn't accurate, the results will not have meaning. So it's really, really critical that you do your MSA first. So the general approach is you're doing that measurement system analysis first, because if that's not right, if your measurement system analysis isn't good, if you can't get good results, then there's no sense in running the DOE, because the data that you get is going to tell you to do the wrong thing. You then want to identify the factors or the variables and the levels that are going to be used, and you lay out the experiment. You figure out how many parts and people and shifts and get the permissions you need to do all the runs on. Then you actually execute the experiments and you look at the results. But when we talk about the MSA for a few moments, we want to look at 3 things on a measurement system analysis. And there's more than 3, but I'm just going over the high-level simplicity items. First, you want to make sure that your measurement system is accurate. And accuracy is managed through calibration. And you can see that my first bullseye is accurate and precise. My readings are correct and in the middle. My third bullseye is also accurate. The average of my readings is going to give me the right value. But it's a little more imprecise because those readings are scattered. Precision is how well does that gauge physically work in that environment where that measurement is being done. And that's repeatability and reproducibility, R&R. So again, in the second bullseye, it's not accurate. It's the readings aren't in the middle where they should be, but they're really clumped nicely together. So they're pretty precise, but they're shifted off. And in the fourth bullseye, they're all over the place. So the gauge is a critical part of knowing that your measurement system can give you good readings. If you are looking at a feature, let's say I'm looking at porosity, number of holes, or scratches, or color. Is it the right kind of black? Is it the right kind of red? If I'm looking at something that's an attribute, you want to have an attribute agreement analysis of 85% or higher. The third thing you want to make sure you have is a good resolution, and that's how well you can read the gauge. So on this here, I have my clock on the wall. It's 10, 10, 35. So I can read this clock to the nearest second. Yay me. So it's 10, 10, 35, but it could be 34 or 36. It's, you know, I've got a plus or minus 1 second with that second hand on there. If I remove my second hand, then I'm removing a level of resolution. I'm not able to read my clock in seconds. I can see that it's 10:10, but is it 10:09 or 10:11? Now it's plus or minus a minute if I lose that second hand. If I take my minute hand off of the clock, then it's 10 something. Is it closer to 9 o'clock or is it closer to 11 o'clock? You really have to start to infer a whole lot more. And this is called the level of discrimination you have in your gauge. So there's a global standard that says your gauging must be at least 10% of the tolerance. This is a global requirement. So if I have a spec that says 0 plus or minus 10, my gauge needs to read to 10% of that. It needs to read to plus or minus 1 of resolution. You need all three of these things together. I look at that as a three-legged stool. If you're missing any one of those three legs, then your gauging system is not going to be robust enough to give you good answers for your design of experiments. So here's some things is when we're looking at figuring out which variables or factors should we use in our DOE. I just got off the phone with a team just before onto this call where they were using 10 different variables in their design of experiments. It's a pretty complex process, but 10 of them. And usually I don't use that many. Usually I only use 2 or 3. And yet we have to remember Alfredo Pareto. So Pareto was pretty cool because 20% of your variables are going to impact 80% of your result. If I've got these 8 variables listed, I've got time and resistance and equipment and humidity, I've got all these different things that are going to make a difference to my result. I don't have to do a design of experiment with all 8 of these things. I just have to be a good guesser to say, well, only 2 out of these are really going to affect 80% of my result. Which 2 are they? And those are the 2 that I need to do my design of experiments around. I don't need to use all 8. I only need to use 2 or 3 of these. And you use your people and your subject matter experts to figure out what those 2 or 3 items are. And for each of these features, time or whichever feature I'm using, I'm going to have it at different levels: a low time or high time, low humidity, high humidity, low temperature, high temperature, low speed, high speed, chemical composition A, chemical composition B, material 1, material 2. So in 2 levels, I normally, like I said, I have that low and high. 3 levels, I might have a low, medium, and high. In our sample today, we're only going to talk about 2 levels, lows and highs. And that's usually more than sufficient if you're not into anything really, really complex. So here's what the team did. This was a real problem in a real factory environment. They had these two pieces here that were bolted together. It was a hinge, and there was this angle, theta, that was created. This spring was hooked up, and this was a teeny tiny angle. I mean, it was a 3-degree angle, 3 degrees, little bitty. Nobody can see 3 degrees. You can't even see it on your protractor that easily. So the team was having a lot of problems. That assembly angle was sometimes incorrect after installing that spring. It caused a lot of rework and component scrap. So we interviewed, excuse me, we interviewed the operators and said, okay, what do you guys think the reasons are? And they came up with a big list. And they said, well, it's got to be the spring itself, how stiff it is or how springy it is. That's called the K factor in a spring, that's stiffness. And then there were 2 different fixtures that they built this into. They'd put the first piece in, the second piece in, they'd lay in the spring, they'd put the little bolt in, and then they'd attach the spring on both ends. So they had two different build fixtures to help with capacity. And then there was two different shifts. Of course, they thought it had to be the people on second shift. So they had a lot more ideas, but thinking of Pareto, these were the top three that they decided to go with. So let's go back to our grid of creating the experiments. So now I know that my three variables are my spring factor, my fixture, and my shift. So how does that work? So I'm gonna keep in mind where those lows and highs are, because I need a low spring and a high spring. I need the first fixture and the second fixture, and I need first shift and second shift. So now I put that in. So my first trial, my first experiment is going to use a low spring with that first fixture on first shift. My second experiment is going to be my low spring with my first fixture on second shift. And this is how I have very scientifically designed my experiments. Now I've got 8 experiments here. So I've done all 8 of them. And that's all there is to it. I've got 3 variables, my spring, my fixture, and my shift. I've got 2 levels, a low level and a high level. And these are the 8 experiments I'm going to run. Now, these plus and minus ones out here are going to be important for us later on, or the lows and the highs, because this is what we're going to use to calculate if these things are having an effect on the angle, because that's what I'm trying to figure out is what's happening to the angle. Is some of these giving me an out of spec angle versus an in spec angle? Now, in real life, there can be accidental bias. So what we have to do sometimes is we have to shuffle up the experiment or randomize it. Sometimes that's not possible depending on how the process is being run, but it's still the same 8 experiments. You've just changed the order of it so that you don't accidentally introduce bias. In this case, we're going to stick through our 1 through 8 and just keep that idea in mind. We've got 4 low springs, 4 high springs. We've got 4 design fixture 1s, 4 design fixture 2s, 4 times it was run on first shift, and 4 times it was run on second shift. So now, here's that same experiment. I have designed my experiment for 3 variables at 2 levels. That sounds really fancy, doesn't it? But in reality, this is all I'm doing. I'm figuring out my low springs, my high springs, and I'm going to run this 8 times with these different settings. It's like making 8 different recipes. So I run it 8 times, and I get my first set of answers. Now, keep in mind, back to the MSA, the measurement system analysis, if I only ran this 1 time, I would only be getting 8 sets of results. This is 8 degrees, 7 degrees, 5 degrees. Those are little bitty angles. If my resolution and my ability to read that angle wasn't great, or my measurement system analysis wasn't working, and instead of a 8.2, I got an 8.6 or a 7.9, that could really blow my data out of the water, and it can really mess up my analysis here. So that's why that measurement system analysis is so important up front, making sure that your gauging system can give you an accurate and repeatable result. So we ran it 1 time, and this was an easy, cheap experiment to run. So they did it 2 more times. So as a total, we did it 3 times. That's each time they run it is called a replication. You don't always get to do replications. In real life, it doesn't always happen because sometimes they're just too expensive or they take too long to do. But in this case, we did it 3 times. So in that first trial, I had the low spring factor on that first design made on the first shift. I had them do it 3 different times. And they got on that angle, they got 8.2, 8.2, 8.2. Well, that's pretty cool. So the average of those 3 replications is over here is 8.2. Now I do have a nifty little Excel spreadsheet that came out of the ASQ statistics division. And so if anybody wants it, just join me on LinkedIn and ask me for that Excel and I'll be happy to get it to you. but it's easy peasy, and then you don't got to deal with Minitab or anything like that. So if I look at my 8th experiment, I had a high spring factor on that second fixture on second shift. We ran it 3 times, and they got an angle of 5.3, 5.2, and 5.3 for an average of 5.3. And we kept this all to 1 significant digit. Now, what's going to happen is when I flip the screen, this average is going to go over to the left-hand side. So I'm going to flip it once, and we're going to bring it back. So here's this average. I brought over the average of the 3 replications. Here's that average column. I brought the average of the 3 replications. What I've done is I've brought over the highs and lows of the springs. So remember, here's the shaded. This was a low spring and a high spring, the first design versus the second design, and then first shift, second shift. So now I've got this average. I've got my low spring, my high spring. Now I want to know is, okay, what made a difference for my angle? I know these are all my angle averages. So that first average was 8.2. That gave me a bigger angle than the last one. That gave me an average of a 5.3. So what I want to do is I want to calculate that main effect of this first variable. I want to know if the spring is making a difference. So how I do that is I get the average of the A high responses. So I've got 4 times did I run this experiment where A was high, where that spring was at the high level. And that was a 5.9, 5.7, 5.4, and 5.3. So I take that, I get the average, and that's 5.6. This is where you're going to want to get your calculators out so you can work along with me in a few minutes. So now I'm going to say, now I've got the main effect of variable A, so it's 3 steps. First, I get the A average, or the average for the high side. Then I'm going to get the side. Now that's where I'm going to be taking the 8.2, the 8.5, the 7.9, and the 8.0, and I'm going to take that average. Now that's the second step. I got the average of the highs. I got the average of the lows. Now the third step is really hard. I'm going to subtract the 2. So I'm going to take that 5.6 and subtract 8.2, and I get 2.6. When we're doing design of experiments, we will be taking the absolute values. We're looking for a magnitude, the absolute value of the effect. And in this case, that distance, that magnitude is 2.6. So this has an effect of 2.6. I'm going to want to calculate what my effect is for the fixture. Did the fixture make a difference? As well as for the shift. Did the shift make a difference? We're going to do that in a few minutes. So one of the things that we look for is when we have the item at the high and the low, we're going to put it on a graph. And if there is a line, if there's a slope, then that means there is an effect. So let's see, let's go back here. So I'm going from a 5.6 to an 8.2. That it's not the same number. So there's some kind of slope going on, 5.6 to 8.2, that there's some kind of a slope happening. It's not 5.6 to 5.6. It's not flat. And we'll see that when we graph this. When we look at the interactions, we're graphing 2 together. We'll graph the fixture to the spring, or we'll graph the shift to the spring, and look at those. And if these things connect, if they intersect like this, then that means there's an interaction. If they're parallel, there's no interaction. But if there's almost a 90-degree or any kind of angularity going on here, something's happening. So let's see what's going on with this. So here we are taking the graph. We're looking at the angle. Remember that angle. So when the factor is low, I get a bigger spring, or I get a bigger angle. So if I get a smaller K on my spring, I get a bigger angle. When I have a higher factor, K factor on my spring, I get a lower angle. I get a tiny angle. So the stiffer the spring, the smaller the angle. And this way I can see that there's absolutely a slope going on. So this is already telling me, this spring has something to do with this. Now let's see what the interaction will be for the other 2 things. So this is where I want you guys to come into play. If you are from A to A, B, C, D, E, F, G, H, I, J. If your last name is from A to J is your last name, I want you to calculate the main effect of variable B. If you are K to Z, I want you to calculate the main effect of the shift. So if you're doing the main effect of variable B, get the 4 averages where it's high. So you're going to get the average of the 7, 9, the 8, 0, the 5, 4, and the 5, 3. Average those 4 values together. That's for the high level. And do the same thing for the lower level. You've got the 8, 2, the 8, 5, the 5, 9, and the 5, 7. You're going to have 2 averages here. Keep it to 1 decimal, guys. And then you subtract the 2 and take the absolute value. The rest of you, K through Z, you get to flip-flop a lot more. You've got the 4 highs, which are going to be 8, 5, 8, 0, 5, 7, and 5, 3. Get that average, please. And then you're going to get the average against the lows when the response is low. 8, 2, 7, 9, 5, 9, 5, 4. And you're going to take those 2 sets of averages and you're going to subtract that and get the absolute value. So hopefully you were able to do that. You were able to get the average of those 4 numbers. Now keep in mind, this is all 4th grade math. Absolute value is what takes you into 4th grade. You learn about absolute values in 4th grade. You're doing averaging in 2nd and 3rd grade, and you're doing subtraction in 1st grade. So these are all 4th grade math level. Here's where all the answers are at. And I can see that my absolute value for the B, which is the fixture, that first fixture or the second fixture, is 0.4. And I can see that the effect for the shift, the first shift versus the second shift, is exactly 0. There is no difference at all between the 2 shifts. So the next thing we do is we take the absolute effects of each of these things. We do the math of each one of these. So I have to tell you, I'm so old that Minitab wasn't doing this stuff when I was doing this stuff. So I had to do all this by hand, which really, that's why I can teach it to you by hand right now, because it was painfully beaten into my brain. This is how we had to do it. So the absolute, so when I take all of the different configurations, so I'm looking at the three effects, but then we're also looking at the interactions between A, B, A, C, and B, C. We put those all into a table. We do the math on all of those. Again, you take it at the highs and you take it at the lows. You subtract the 2 and you get that difference. And you get that absolute effect. And you rank them from highest to lowest. And in this case, you can see the spring factor is significantly high at 2.6. And the next biggest thing is the fixture itself. So here's what it looks like on a graph. So here I now have the spring lined up. And you can see that that's got a pretty heavy slope to it. You can see my fixture. My fixture doesn't, it's got a bit of a slope, but nothing that I would call significant. And the shift has no slope whatsoever. So when I'm looking at this, I'm thinking, okay, there's definitely the spring, the K factor, the springiness of the spring, which is definitely affecting my angle. And as I can now start to either sort out my springs or tell my spring supplier I want a different range of K factors in those springs, I can now better control how that part is going to be produced. And that's exactly what we were able to do. So these are the interactions for, this is doing the rest of the graphs for the interactions. So this is for the A times C, which is for the spring and the shift. And you can see here that these are parallel. They're right on top of one another. There's no 90 degrees from each other. So because, and remember, a strong interaction line is going to be seen by non-parallel lines. They're all absolutely parallel with each other. They're laying right on top. Therefore, there was no interaction between the spring and the shift, between the spring and the fixture, or between the fixture and the shift overall. So there were little or no angle or perpendicularity indicating no interaction. So there's a lot of combinations out there. In this particular graphic that you can see, this shows 16 experiments. And this is using 8 variables at once. There's a lot of shortcuts that can be taken in the bigger experiments because some of these things end up being duplicated in the data. When you're getting into these bigger, hairier things, you're going to want to use software to help you figure that out. If you have many variables or differing levels, there are other design of experiments formats that you can use. And in this case, if I were to use 2 levels, a low and a high level, for 8 variables, that would be 2 to the 8 experiments. That would be 256 experiments I would have to run all the way down and randomize. And no one's going to do that. That's just crazy. So like I said, there are shortcuts now that can be taken as this science has really taken off in a positive manner. And these are fractional factorials. There's 5 or 6 different versions that can be done out here. And all of the graphics, all of the interactions and the effects are still done the same way. You look at the data when the levels were high versus when the levels were low. If you only have one set of results, you're subtracting that from the other, and you're looking at that magnitude of difference. That's all you're doing. You're taking the average of the high minus the average of the low at the high level minus the average at the low level, subtracting the 2, and you're looking at that magnitude of difference, that effect that's being had. So what we've done is we've walked through an overview of the basics of a design of experiments. We had 3 variables. We had 2 levels, a high and a low. So that was 8 experiments, 2 to the 3rd power. 2 times 2 is 4, times 2 is 8. And we want to see how it worked in concept by using using the math, getting the averages at the high, averages at the low, subtracting the 2 to seeing what the effects of each variable were. And that allowed us to then figure out which feature was having the biggest effect on our little bitty teeny weeny angle. That's what I had for you all. So I am going to take this out of my show mode, and I'm going to see what questions people have, and I can do to answer them for you.
Well, I want to comment, JD. That was actually a really, really good explanation of DOE.
I'm trying to get back to this. There we go. Well, thank you. I appreciate that feedback. We had fun with it because it really is 4th grade math. That's all it is. And then it's graphing the pictures.
JD, I'm totally impressed that you did this design of experiments without conducting the formal factorial analysis, in an easy way. So that's absolutely great.
It didn't have to. Yeah, that was overkill, right? I mean, you get people out of you get people in the manufacturing environment that are trying to solve a problem, and some people can get so theoretical, and it gets in the way of solving the problem.
Right. So let me ask you this question. Whenever we talk about design of experiments, there are 2 major phases to complete. One is identify the major parameters that affect my output, and the other one is what's going to be the setup to obtain optimization. But there's another new technique And my question is if you have seen it, VTA, variation transmission analysis, in order to obtain robust setups, robust processes.
Yeah, and I would use VTA before I'm creating this tool. I use more after the process is released. So I'm trying to diagnose a problem in the production environment. VTA I would be using more for designs for Six Sigma, or in terms of design for analysis, trying to figure out that optimization prior to releasing my production process, so that I can optimize the settings before I unleash it upon my unsuspecting production teams.
Okay. And in terms of confidence and reliability, the setup that is provided by Minitab in terms of the response surface, settings, and VTA, which one do you think is more reliable?
I have no idea. And I don't know that it matters. When you get a magnitude or you don't, what really matters is the accuracy of your measurement system. You've got the data.
I agree.
Yeah, you got the data results coming out.
Yeah.
And if those are good, you're just subtracting the average of the highs versus the average of the lows, and you're looking at that magnitude.
Yep. Totally agree. And my last question, because I need to let the rest of the group to ask you questions. It's very interesting presentation. Have you met Wayne Taylor, the VTA software developer?
No, that name's not familiar to me.
No, this guy is living in the area of Chicago.
I'm living in the area of Detroit. Maybe he'll come to Sweet.
Yeah, this guy used to work for Baxter in the old days, and he developed the VTA software.
Strong people out there on this topic.
Okay.
Try to keep it simple, so that it's very practical and easy for folks to do in their work environment.
Yeah.
Totally agree. Totally agree.
Yeah, it looks like more than Taguchi than a traditional, right, JD?
Yeah, it's pretty much Taguchi based. Yeah.
Right. Thank you. Yeah, we worked in Taguchi in 1993. In 1993, we just moved from the wave solder to the surface mount technology.
Mm-hmm.
Yeah, and we use Taguchi for using the different solder paste that we use for electronics at that time.
Yep, I'm in electronics right now, so I understand that really well.
Thank you, JD.
This is an excellent presentation to the people that never seen design of experience, so you can explain this way and they're gonna get it right away.
I can hope.
Yeah, very, very interesting. Very easy to understand. That's correct.
Yeah.
Like I said, it's fourth grade math. It's not higher. It's not any higher than that. And I think people that do design of experiments, they try to keep it secret so that they're the only ones that can do it.
Yeah.
You're right. You did a great job in putting this presentation, JD. Thank you.
My pleasure.
Thank you, JD.
Any other question from the group? Evaristo?
Michael?
Michael,
Steven?
yeah. Steven? Yeah.
Very good presentation.
Yeah, actually, I was going to say that I agree. It's a great presentation. When you see the title, DOE for fourth graders, you don't believe it. But now,
yes, I know.
yeah, and actually, I'm impressed of how you shows a fourth grader, not a first, second, or third, and you explained that very well as well.
Yeah.
Well, I have to take you to fourth grade. If not, I could keep you at third grade.
Exactly.
Like
thank you very much. Excellent presentation.
Very nice presentation.
Muchas gracias, señor.
I really enjoy your presentation, JD. Really,
Yeah,
it's
JD,
great.
it's another presentation, excellent presentation, like before, the one that you provide us. Thank you very much.
You're welcome. How many people were there on the session?
8.
Let me see. Yeah,
It was 8.
we
Okay.
have 8.
Thank you. Very good.
And,
Thank you, AD.
and JD, you are very welcome to come back again to give us, more presentations in ASQ El Paso section 1401, okay? We were very satisfied with your previous presentation, and now we are absolutely, happy to see, how you can do complicated concepts simple.
We try.
Thank you very much, AD.
All right,
All
good
right,
night,
you
everybody.
guys have a great evening.
Thank
You
you.
made me use
There's
this.
your
Very
protractor.
nice.
Can you see 2
There it
degrees?
is. Yes, I got my degrees. Thank
Thank
you.
you.
All right. Thank you,
JD.
guys. Have a great day.
Thank
Bye.
you. You
Bye.
too. Thanks. Bye.
Yeah.
Woohoo, Mac. Luce. Woo-hoo-hoo.
Hello.
I got my degrees.
You've got everything saved, Jack?
I'm doing that.
I'm afraid to leave because I fear I might interfere.
So before you go, Keith and Hector,